This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello, this is Justin Byer for Software Engineering Radio, and today I'm speaking with Thomas Graf about eBPF. Thomas is a co-founder of Cilium and the CTO and co-founder of Isovalent, the company behind Cilium. Previously, Thomas worked at Red Hat and Cisco as a Linux kernel developer on the Linux kernel and various other open source projects. Welcome to the show, Thomas.
Thanks a lot for having me, Justin.
Yeah, of course. So just to start off the show, I want to discuss a little bit of a baseline before we dive into the eBPF. I want to talk a little bit about how the Linux kernel is structured. So from a high level, can you kind of discuss, how does my user space program interact with the Linux kernel and a little bit about the internal structure of the kernel?
Sure. The kernel is what typically sits between an application and hardware or appliances. And it is there to abstract the hardware away so applications don't have to care about what hardware you're actually running. And that could be real hardware or it could be virtualized hardware. And the kernel is fundamentally event-driven, so it will only do something if you ask it to do something, right? It's not magically doing something. There are maybe some timer-related things that are happening, but generally there are system calls that are happening from the applications. For example, hey, I want to open a file, or hey, I want to do a TCP network connection, or there is hardware telling the kernel, I have something to read, or I have a network packet that has just come in, you need to do something about it. So the kernel is there to act on those events and to connect hardware with applications to, for example, allow an application to open a TCP connection or to store a file or to read from a file and so on.
Okay, so it's event-driven. We're leveraging syscalls from user space into kernel space to drive those events. Mm-hmm. So we're going to dive a little bit into where eBPF fits in that. But before we get there, I just want to talk a little bit about how are changes actually made to the kernel.
So if we specifically talk about the Linux kernel, which we do in the context of eBPF, it is an open source community. It's hundreds or thousands of kernel engineers or kernel developers who will make source code modifications. I would call it relatively old school, so it's still using mailing lists. It's not using Slack. It's not using GitHub yet. It's using Git, or Git was actually came out of the kernel development movement. So you have hundreds or thousands of people that are making code changes that then run on millions and millions of devices, from high-end servers to really small embedded devices, which leads to this interesting scenario that have many different interests, and they all have to agree on that a particular change makes sense for all of them. So all of this creates this very unique, very interesting kind of group of people that all have similar goal, but they're not all caring about the exact same thing.
Yeah, so it's almost like that debate you get when you have the 500 distributions of Linux of which one do I pick. You're still at the kernel level trying to summarize all of those higher level specific like Ubuntu changes or Debian changes or Arch changes. And you're trying to kind of boil that down to core essence and say, okay, but this is the actual functionality we need in the kernel.
Mm-hmm. Exactly. But the huge benefit is that if you have something in the kernel, it's available everywhere, right? Linux is everywhere these days. So if you manage to get functionality in, it means you have this available on any smartphone that is Linux based, on any Linux server, on most home appliances that are Linux based. So the gain you get from something integrated into Linux kernel is huge, obviously.
So then kind of diving into eBPF, how did that actually get introduced into the Linux kernel?
This is very interesting. eBPF kind of origins from BPF, which is the older, more natural form of it, Berkeley Packet Filter, which is older than I am. So it's very old, and it is the original packet filter from the BSD days. It's a small coding language that allow to write filters to, for example, if you run TCP dump, to specify with which packets should actually be displayed, or if you have a raw socket, which packets should be received on a raw socket. So it's something low level in the kernel that was used to select a subset of network packets. And eBPF is the extended version of that, and the motivation for it was that it became harder and harder to find consensus among all of the Linux kernel engineers, because a certain change may make sense for a Google or a Facebook or one of the other very big companies utilizing Linux for high-scale environments, but it may not make sense for example, embedded systems. And this led to a motivation or to a discussion is kind of into the way of, can we make the Linux kernel programmable? And this is where eBPF started.
Okay, so just to kind of go a little bit back, when we're talking about packet filtering, what actually is that? Because I know some of our listeners may not be super familiar with that lower level network stuff.
Yeah, so packet filtering is done on multiple occasions. The most obvious one is for example, a firewall, right? If you want a security firewall, you need to be able to do packet filtering to decide, should I allow this packet or should I not allow for this packet? The example that most people are probably aware of is IP tables, where you have a rule such as, I want to allow SSH and I want to drop everything else. And I want to allow all of my reply packets, and that's it. Like that's a typical stateful packet filter. But there are other cases as well. One is something I've already mentioned, which is TCP dump. You can run TCP dump to capture network packets on a network device and display them, for example, for network troubleshooting. In this case, you also want to apply a filter and, for example, say, oh, I only want to see network packets on port 80, or I only want to see TCP packets with the SYN flag set, and so on. Those are typical examples of a packet filter.
Yeah, and commonly I hear it discussed, TCP dump underlying something like Wireshark to display the actual captures and view the PCAP files and all that kind of stuff.
Exactly. TCP dump is kind of the raw form, and then Wireshark is the GUI on top.
Exactly. So you mentioned how eBPF is kind of this programmability in the Linux kernel. Can we kind of talk about how eBPF is actually working under the hood, like integrated into it? Like, how is that actually hooking into the kernel?
Absolutely. eBPF by itself is a bytecode language, which is restricted but relatively general purpose. So you can write programs which contain logic. The kernel then provides a whole set of hook points to which you can attach those programs and run them when a certain event happens. And this suits nicely into the event-driven architecture of the Linux kernel. So for example, you can run a BPF program when a network packet is received, or when a network packet is transmitted, or when a system call is being made, or when a trace point is passed, or when a user space probe function is called, and so on. So the kernel provides a set of hook points which you can extend and run a BPF program, and that program can then return a verdict to instrument or to indicate to the kernel what to do at that hook point, how to proceed further.
Okay, and we are going to dive a little bit into those discussions about what those hook points are and stuff when we discuss a little bit later about writing eBPF programs. But I just kind of want to talk about, what are we talking about with complexity of eBPF when we're talking time cost, memory cost? If I want to write an eBPF program, how much of a hit on my system am I going to see?
So eBPF is specifically designed to be as efficient as possible. And for that reason, it actually comes with a just-in-time compiler, which means that even though you're loading generic bytecode, portable bytecode into your Linux kernel, the just-in-time compiler will compile that and translate that into whatever your CPU runs. So from an efficiency perspective, you're very close to execution speed as if you would recompile the kernel. eBPF programs are typically not very complex. There's even a complexity limit to programs because from a kernel perspective, you don't want to allow users to load programs which might then stall the kernel. So eBPF programs have to be fundamentally secure, and having a known complexity or an upper complexity limit is a key part besides other aspects.
Yeah, and we'll dive into some of those restrictions a little bit more later on. I know there's some restrictions around looping and pointers and all that kind of stuff. So when you're saying the just-in-time compiler, though, are you talking about, is that where LLVM kind of fits into that layer?
So there's two layers of compilation that happen. First of all, BPF is an assembly-like language. It looks very similar to x86 assembly. And yes, you can write the BPF bytecode at that level, but that's not what you typically do. You typically use C or a pseudo-C language and then use LLVM to compile pseudo-C into BPF bytecode. And then the kernel will translate that again from the generic bytecode into, for example, x86 eBPF.
Okay, and who's maintaining all of this stuff within eBPF? Because it sounds like there's definitely a lot of underlying functionality that's dependent on constant maintenance.
Exactly. There's multiple layers that are stacked on top. Like if we start from the very bottom, there is the eBPF subsystem in the kernel, which is maintained by Daniel Borkman and Alexei Starovoitov and Andrei. Sorry, Andrei, I completely forgot your last name, but 3 maintainers on the eBPF kernel side. That's what's in the kernel side. This is the engine. This is the chit compiler. This is the verifier, which we'll talk later about. These are the hook points, everything that runs in the kernel. And then there's a libBPF, which is also maintained by the kernel community. That's low level. And then on top of that is various tool set, like for the compiler suite, LLVM, and then tools like Cilium, BCC, BPF traits, which are higher level tools. They're still very much in the eBPF ecosystem because most users will not typically write BPF programs themselves. They will leverage a tool that sits on top that provides a more user-friendly way of actually using it.
Yeah, and we're going to discuss BPF traits and some of those other tools when we start talking about troubleshooting the programs you're writing in BPF.
Mm-hmm.
But I just want to give a couple examples of some functions of writing an eBPF program. What's going to motivate me to write one of these things rather than just depending on a Cilium or something like that?
I think the vast majority will not write eBPF programs. I think in the beginning that was very much the case. A lot of the high-leveling tooling did not exist. If you look at the typical use cases to leverage eBPF, it's tracing, it's networking, it's security. For all of these major use cases, a tooling exists, right? If you're looking into profiling and tracing, you will use something like BPF trace, and only if there's no specific program in the huge set of in the huge library of existing eBPF programs, only then would you actually go in and write your own eBPF program. The learning curve is definitely high. Similar on the, let's say, the system call security side. There's seccomp, there's a seccomp BPF. There's no real reason why you would go down to the eBPF layer. You want to benefit from the power of eBPF, but typically you can make full use of it without actually fully understanding eBPF. So I think unless you're looking to start a new eBPF project, most likely you will start out with some of the higher level tooling first.
Yeah, so unless you're trying to dive straight into, I'm writing XYZ project and I need to do this kind of interaction with the kernel and the kernel devs won't accept my patches, that's when you might start looking at using something like eBPF to do that. So just kind of changing direction a little bit. The other, acronym that I hear thrown around when eBPF is discussed is XDP. Can you kind of discuss what that is and how that kind of fits into eBPF?
Yeah, so XDP is the Express Data Plane. And in a nutshell, it's the ability to run a BPF program inside of the network driver of Linux. And why would you want to do that, right? I think that sounds a bit crazy. If you come from the networking world, it's actually not crazy. In the networking world, it's several use cases quickly evolve around how many packets per second can you handle. So, for example, if you perform high performance load balancing, or if you perform DDoS mitigation, the type of measurement you care about very quickly is about packets per second. Like how many packets per second can you load balance? What type of DDoS attack can I sustain from a packets per second perspective? And in that context, it's actually very useful to run as close to the hardware as possible. So you want to be able to do packet filtering or load balancing without actually going through millions of lines of kernel code first. In that sense, XDP comes in and it allows you to program network logic incredibly close to the hardware, which means that you pay the least amount of overhead before you get to the BPF program that does the actual work.
So it's almost getting an eBPF insert before drivers, or at the same level as a driver would be getting within the networking hardware?
It's at the same level as a driver, but you still have, for example, instead of, first of all, creating what's called an SKB, a socket buffer, which is the generic abstraction of a network packet. Inside of a driver, every driver will have its own view of things. It's still very hardware specific. And then the Linux kernel has this abstraction layer on top, which makes everything generic. And that is already pretty costly. You do memory allocations and so on. XDP allows you to run logic before you pay this big first cost. It means that you don't have access to a lot of what the kernel provides. A lot of for example, there's no IP or TCP or anything like that. You're talking about raw network packets. But if you do load balancing or if you do DDoS mitigation, you don't need any of that. All you want is to be able to look at the packet as early as possible and either do a load balancing decision or say, I need to drop this packet because this is part of a DDoS attack.
Okay. And just kind of diving into, let's say, the DDoS example a little bit, or the load balancing example a little bit. How am I passing that information into XDP to say, yes, these packets with this signature need to go away, or these packets with this signature need to be directed to this IP address or something to that effect?
Exactly, yes. This is where the generic nature of BPF comes in. So BPF consists of the program aspect, which is the actual program code or logic. And then the second big aspect is BPF maps. Those are data structures. They can be hash tables, that can be LPM, longest prefix matches table, and so on, like a wide set of data structures. And typically the configuration of a program is in those maps. So if you look at, for example, a DDoS mitigation program, you would typically store the IP ranges or the CIDRs which you want to drop in an LPM table, and your XDP program will basically parse the network header, look at the source IP address, and then see if there is an LPM match in the LPM table, and if so, drop the packet. So that's the program logic is relatively simple, and the actual configuration on what you want to drop is actually encoded in the eBPF program, which means that if you need to change what you want to drop, you're not rewriting the program, you're only changing the content of the BPF map. And this BPF map can be modified, both read and written to from user space as well. So there's a system call that allows a application running in user space to take control over that eBPF program and the eBPF map.
Okay, so I could almost have my user space program running, DDoS mitigator that's getting network calls with CIDR information from my security infrastructure. And that's then updating the map in BPF. And then my XDP program is referring to that BPF map and then acting based off that.
Exactly. So you have the control of what we would typically call the control plane, the controller portion is in user space, typically written in something like Go or another high-level language, and the actual data path that needs to be really fast, handling millions and millions of packets per second, that is in BPF, XDP, very, very low level.
Okay. And you mentioned LPM tables in passing there. I'm assuming you're talking about longest prefix match.
Exactly.
Can you kind of discuss what that is? Because I'm not sure how many of our listeners would be super familiar with that.
Yeah, this is something quite networking specific, and it's the notion that if on the internet you have routing, and routing is the logic that decides where network packets need to go. And in order to avoid that, every single device on the internet needs to know every other device on the internet, there is something called subnets or routing, which means that some devices will generally know in which direction the packet needs to go. And then the closer you get to the destination, the more accurate information you have. In order to implement this, you have something like a longest prefix match, which means it will always match on the most accurate, the most exact version of the information you have. So if you know about the exact destination IP, it will match on that. But you can also add an entry into that, something like an IP 10.0.0/24, which means the last 8 bits could be anything, and it will only match on the first 24 bits. That's longest prefix matching. It's something very networking specific.
Yeah, so usually I hear like the simple example is you kind of mentioned, you have that 10.0.0.1/24, and then you have that 10.0.0.0/8. The /24 is what's going to win because it's that longer prefix. It's more defined, more specific.
Exactly.
So just kind of moving along here, you kind of talked about XDP fitting in at that, hardware interface NIC level, network interface card, and eBPF kind of underlying that as the logic. Is there any other use case where you're going to want to start using XDP in combination with eBPF?
I think the prominent use cases right now are DDoS mitigation and load balancing. And load balancing, primarily what we would call north-south load balancing. That's typically packets coming into a data center or into a set of machines. These type of load balancers are typically exposed to the internet, so they're subject to a lot of traffic. And you typically have a small number of load balancers and then a vast number of servers behind those load balancers. For those, XDP is ideal because what you typically do for those load balancers, you receive a packet from the network card, you do something to the network packet, and then you send it out the same network card. So you're not actually delivering it to an application running on that same server or on that Linux machine. All you want to do is manipulate the network packet to do the load balancing, so change certain fields in the network headers and then send it out again. Those are the prime use cases for XDP, but there are definitely others as well. There has been talk about doing early demux in XDP. There's definitely cases where you can do something like encapsulation in XDP. There are cases where I've seen people build NAT4.6, so the translation from IPv4 into IPv6 and back, for example, for IoT. A lot of IoT devices will only do IPv6, but the actual backend applications are written in a way that they don't understand IPv6 and so on. All of those low-level network functions can be done at very high speeds with XDP. And when we talk high speeds, that usually also translates to very low power consumption per operation. So it's not necessarily millions of packets per second, it's also just watts per packet in that sense. So if you have very little compute power available, XDP is very interesting as well.
Yeah, so that's where it almost has that perfect fit for the IoT environment where, if I want to stick X IoT device in someone's refrigerator, I don't want them changing the batteries every single day because they're not going to buy my product anymore if that's the case. Let's kind of talk about how we write these programs, how I'm writing an eBPF program or an XDP program. Just from a high level, what kinds of libraries can I use to write an eBPF program, for example? And then we'll kind of discuss about writing XDP programs.
Yeah, so first of all, I think the first category is to not even write an eBPF program, but to just leverage one of the tools. I want to emphasize that enough because I think there's a perception that, I need to learn about eBPF. I think that's great, but you can leverage all of its powers without actually having to write your own program. If you want to write your own program, there's a set of libraries that you can use, starting from there's a Rust implementation, so you can write programs in Rust. There are ways of writing eBPF programs in Golang. Typically, the actual program code is always in pseudo C. So I use always some form of C code that is it's kind of a limited set of C. So you can't do arbitrary Cs. Arbitrary C. You can do function calls by now. You can do what's called bounded loops, but you can't loop forever, for example. So it's a subset of C that you can use. You write that code and then you either use LLVM or more recently GCC also has BPF support, and you run it through the compiler and that will generate you the bytecode. At that point, you will load that bytecode into the kernel using the loader infrastructure. There is libePF, there is TC, there is BCC and a couple of other loaders. This is the code that will take the BPF program and load it into the kernel. So it will make sure that the BPF program has the proper ELF headers and all of that to make sure the kernel actually understands. And then this will load it into the kernel. At that point, the kernel will verify it and make a judgment whether the program is safe to run, and then either complain or successfully load the program.
Okay, so that's a lot to unpack there. So let's just kind of take this like one bit at a time here. So first, we're writing our code using some libraries. So essentially, we're creating some type of pseudo C. And I've also heard the library for Python BCC thrown around, handling a little bit of that compilation automatically for you. So then you're compiling it into bytecode and you're putting it into an ELF format. Can you kind of dive into what that is and why you're putting it into that format?
Yes, because you need to, one aspect is just the code itself, and then another aspect is you need metadata around the program. So you need to understand what BPF map does this program use. You need to understand how the program should be loaded. So at what hook point should it be attached to? You need to understand who is loading this program. And then more recently, also eBPF signing. So the signature of the BPF program is also being discussed. So there is the program itself and then a bunch of metadata that needs to go along with it. And that needs to be standardized. So kernel and user space need to understand how this information is encoded. So both sides can actually understand it.
Yeah, and ELF is usually a common format or a common standardized format in the Linux world for passing these binaries around.
Yes.
So then it's and we're going to discuss those hooks and trace points and stuff like that a little bit later. But so then it's getting loaded in. So how is that loading process actually working? So is that something, a kernel syscall that's pulling that in? Is there a loader within the kernel that's doing this?
So it's a system call. There's the BPF system call that you can use to load the program. The same system call is also used to create maps, to attach to maps, to pin maps. We can talk about that as well, what that is. to access maps, to write into maps, to read from maps, and so on. But there's one system call that you do to load the program. So you could say, here is my program. This is the ELF. Attach it to, let's say, the TC layer. That's a traffic control layer. And I want to run this program every time a network packet is received on ETH0, for example. And you tell this to kernel. The kernel will take the program, verify it, and attach it to that hook point. And the moment it is attached, the next network packet that is arrived will flow through that eBPF program.
Okay, so it's still got that verification layer. So can we kind of talk about what that's doing? What is that checking for? How does that kind of work? And then what kind of feedback is it giving to you as a developer if something's wrong?
Yeah, I think a lot of listeners may kind of be wondering at this point, why are you going through all of this? Why aren't you just loading a Linux kernel module? The Linux kernel was always extendable. And the very big difference between a Linux kernel module and eBPF is safety. eBPF is from design secure, which means that you can't load arbitrary functions. So it may sound like making the kernel programmable means I can call into arbitrary kernel functions. That's not true. You can call into what's called eBPF helpers or helper calls. It's a subset of the functions that the internal kernel API offers, but in a stable manner. So even across kernel versions, it will be the same. So it's the amount of complexity and the amount of operations an eBPF program can do is limited, and the verifier ensures that this is met. So a couple of checks that the verifier does. It will first of all check the overall program size. So you can't load a 50 megabyte program into the kernel. The kernel will reject it. There is a agreed on upper limit for BPF programs. And then the kernel will do a verification of every single branch that exists in the program. So it will calculate all the possibilities that the program could go into, and it will make sure that all of those paths run to completion. So it will ensure that nothing can loop forever. It will also make sure that nothing is uninitialized. So every single piece of memory has to be initialized, and so on. There's a long list of things that it will do to ensure that an eBPF program, even if it's harmful, cannot crash the kernel and it cannot stall the kernel. So even if somebody has access to the eBPF system call, which is typically protected by privileges, but even if somebody loads a malicious program, the verifier will ensure that the kernel can continue running. So that's a huge, major difference between a Linux kernel module and eBPF.
Okay, so it has that almost implicit benefit of, even though it's because it's event driven, there's no way to completely stall the kernel on an event. So, if I hook into network traffic, I can't write a program that just does an infinite loop and basically takes your entire server down if I got on it.
Yeah, exactly. You can still do things like drop all your SSH packets and lock yourself out, but you cannot do something like let's just loop forever and then my kernel will stall.
Exactly. So you can still shoot yourself in the foot like everything with Linux, but you can't completely take the system down. So what is the benefit of this over a user space program? I mean, generally with a user space program, or even, a kernel module, as you kind of mentioned, the benefits, it's more safe. But from a developer perspective, why am I going to go towards eBPF over writing a kernel module or writing some user space program to do this?
The only occasion where we actually want to do this if you need to run it in the Linux kernel. So when do you need to run in the Linux kernel? One aspect is you are seeing everything that the application is doing. So, for example, if you want to implement what's called container runtime security or system call filtering and restrict the number of system calls a particular application can do, you need to run in the Linux kernel because system calls are being made through the Linux kernel. So you need to run as part of the Linux kernel. Or if you want to get involved into networking, you either need to do this in the kernel or you need to do something like user space networking where you bring the hardware to user space. But typically the main reason why you want to write an eBPF program is if the context you need and if the use case you have needs to be solved in the kernel. That's why eBPF is there. It does not make sense to port arbitrary applications into eBPF.
Exactly. So there's no reason to port my Hello World program into eBPF because, it works just fine in user space. And it's really starting to get into that concept of if you need to start intercepting sys calls, that's when you need to start going into the kernel.
Mm-hmm. But one other good example is, for example, if you want to do performance troubleshooting of your applications, like you can either go on and make modifications to your application and, for example, add trace points and add print case or printfs, or like link in some debugging library that will do profiling for you. But that requires you to recompile and restart your application. With eBPF, you can do a lot of this for a already running application, because the kernel is always in a position to observe what the application is doing. And this is where it gets really powerful. The kernel has access to observe everything that is going on the system, and it can take control over everything that's going on in the system in a completely transparent manner without having to change any application code. This is where a lot of the benefit is coming in. If you look at a lot of the eBPF talks around, for example, tracing and profiling, it's about performance troubleshooting on live applications in production, where you cannot restart them. You cannot run a debug version of this, but you still need to figure out why your application is slow. You still need to figure out your distributed application running on hundreds of servers, what is consuming CPU, like which functions are consuming how much CPU. Typically, if you run this on your laptop, you would link in some debug library or something that will give this information. You cannot do this for the application running in production, right? This is the key benefit of the kernel. It can see and control everything that's on the system.
Exactly, because you can't push a debug version of my giant distributed mail client. Nobody's going to like it if all of a sudden their email has a bunch of error messages popping up on the client side. It's bad user experience. So just kind of driving back here, you kind of mentioned, we've talked a little bit about BPF maps. So you mentioned pinning maps. Can we just kind of discuss what pinning a map is and why you're going to do that?
Mm-hmm. So as we mentioned, BPF maps contain the state of the application or configuration. It's a set of data structures. That just immediately brings up the question, who owns these maps, right? So you have the BPF program, it's running in the kernel, but the BPF program can actually access multiple maps, and the map can be accessed from multiple BPF programs. So the map itself cannot be owned by the BPF program. You can, for example, have a program on the network level and another one on the system call level, and they can both interact with the same eBPF map. We also said that the eBPF that the Linux kernel is event-driven, and a user space application may not live forever, which means that it opens up this difficult question: who owns the eBPF map? At what point is it no longer used? And for this purpose, it was decided that we need to somehow pin that to the file system. So it needs to have some representation where you can see this BPF program exists or this map exists, and there needs to be some way to release that resource again. So kind of delete the map. And for this reason, there is a BPF file system, and every BPF map can be represented on the file system, and you can access it through a file descriptor. This allows a program that loads the BPF program, or like a user space process loading the program into the kernel, to actually quit and terminate and then start again and access the map again. So you don't need to have a process running all the time in user space, and as soon as that process would terminate, all of your programs would be gone. All the resources, all the programs, all the maps are pinned to the file system, so they will exist even if the user space process terminates or crashes or something. This is why pinning exists. It's also a way for other programs to discover the maps. So you can have multiple user space processes, and they can discover a map by just opening the file system and opening the file, basically.
Yeah, so your program's coming up and it's able to do that, file descriptor, doing an open sys call on that actual file that's underlying. And as you kind of said, and we might discuss this a little bit when we discuss containers, but, they're ephemeral. They can go away and disappear and go everywhere. And they still need to be able to access these things without getting rid of that file. But that brings up a question. Is there any kind of garbage collection on this? How does it know this is no longer, needed anymore?
No, not really. It's the responsibility of the program loading or the process loading the program to also remove it again. Typically, PPF programs are a very crucial part of the overall system. If the eBPF program does load balancing or, for example, container networking, you want that to continue running under all circumstances, because if it not being available could have tremendous consequences. So the worry is always that some failure in user space could affect what the overall system is doing. So there's no automatic garbage collection. It's the responsibility of the process which loaded the program to also remove it again.
Okay, so essentially, whatever loaded the BPF program through the BPF syscall is also responsible for unloading the BPF program and cleaning up any of the mess that it created.
Yes.
Okay, so that also brings up another question that I have. So we've mentioned throughout like trace points, kprobes, ktrace. What are these things within the kernel that we're actually hooking?
It can be almost everything, actually. So it's actually a very, very good question, because the number of hooks that exist are continuously being extended. They already range from, if we start from top, user space probe. So even your regular applications processes running in user space, you can define a so-called user space probe and say, if this function inside my application is called, then invoke this eBPF program. This is how you can profile your own user space application. You can do kprobe. So for any kernel function with a known symbol, you can attach a BPF program when that function is entered and when it exits. For any trace point, and the Linux kernel system or the Linux kernel provides or maintains a long list of trace points, stable names to which you can attach to. For example, network packet is being transmitted on the IP layer, or block storage access from like the generic block storage does a read or does a write, and so on. All of those are generic trace points. Then it goes all the way into very, very specific scenarios, such as TCP congestion algorithms. So you can write programs that optimize how TCP congestion algorithm works. Or every system call that is being done, you can attach a BPF program to. Or XTP, as we mentioned, like very networking specific. Or socket operations. So sockets are used to do network operations of the application. You can attach eBPF programs to. eBPF is really becoming this very general purpose programmability layer, and is making its way into almost all of the kernel subsystems. There is an eBPF program to do infrared frequency reprogramming or something like very niche, right? Very niche, but it shows the wide usage of eBPF. I think in the future it will even go as far as code that is currently written by kernel developers natively and merged into the Linux kernel in the future might be written in eBPF because it will be more secure. It might be hard for us to believe, but even kernel developers will make mistakes. Even kernel developers will include bugs. And having a verification layer that is another safety net will have huge benefits, because any bug in kernel code will affect millions and millions of users out there. So I think eBPF is really becoming this very general programming layer for the Linux kernel in general. We're talking Linux kernel right now, but I think it will actually make its way outside of Linux as well. We're already seeing early on signs of this. Like there's a FreeBSD port. There's been tweets from Microsoft about this. So I definitely, eBPF will become much bigger and will make operating systems in general programmable.
Yeah, because it's almost providing that safe abstraction layer within the kernel. Not really an abstraction, but a way to hook into the kernel in a more safe manner than people were doing when they were writing modules, or like in the Windows world when you're writing, really low level drivers that are hooking into it to do some of these things. It gives you a little bit of verification that you aren't getting with those other things.
It also makes programming easier, because if you write a Linux kernel module, for example, you are using internal kernel APIs like functions or libraries that the kernel internally provides. There is no stable guarantees given by the kernel community that these functions have some sort of API or even API compatibility, which means every kernel version may break this. So you will have to adjust your kernel module code for every kernel release. You might even have to release it for different kernel versions and so on. eBPF has this abstraction layer in between that. Yes, you can, for example, call a function that will get you a random number back, but this is a stable function that you call. And even if the backing implementation changes, the actual helper call, that API will always remain stable.
Yeah, so kind of going along that example, if, for example, the kernel changes how you're getting a random number and they change the function name from get random to get urandom, now that's a breaking change for your module, and now you're putting a nice little if statement in there to check and see which kernel versions you're on and whether it's supported or not. But from an eBPF perspective, you can have just a simple, get BPF random, and whether it goes to you random or dev you random or dev random, it doesn't matter, because from a developer perspective, you're getting the same API call between.
Exactly. For those who have written kernel modules in the past, a kernel module typically is thousands of preprocessor if conditions, if kernel version X, if kernel version Y, and then different code. It's a mess, right? It's a mess.
Yeah, and it's horrible to maintain because now you have to watch the kernel mailing list and, almost have a little regex filter looking for whatever function names you're using to see, did someone propose a change to this? Did someone propose a change to this? And then giving that feedback to say, no, don't do this. Or, ooh, wait, I got to fix my entire module now and re-release. But kind of going back a little bit, you'd mentioned the concept of hooking to anything with a known symbol in the kernel. I'm not sure how many of our users would be familiar. What does that mean when you're saying a known symbol?
So if you run your kernel, typically you don't have the symbol table available, which means that kernel functions are behind arbitrary addresses, right? Like memory addresses. And in order to understand where a function starts or where code for a function is located in memory, you need something like a symbol table. And the symbol table will map the name, for example, system call write, like where is the implementation for the write system call, and will contain the memory address. Where is that code for that system call in memory? And if you have that symbol table available, you can basically say, I want to run an eBPF program when the system call function for write is invoked or when it returns. And this is what kprops is about. For this to function, you need that symbol table, because as a human, you don't recognize the symbol or the memory addresses, but you will recognize the human readable function names.
Yeah, and even if you do know the memory address specifically because you sat there and debugged it, the problem is when you have stuff like address space layout randomization turned on, which should be turned on in your kernel and you shouldn't be turning it off, you still need that symbol layer to do the symbol table to do the translation for the address for you, since hard-coded address really doesn't work anymore.
Exactly.
So we've kind of talked about writing these programs a little bit. So how am I going to troubleshoot this program if I'm writing one? Are there tools that I'm going to use to do that?
Yes, I think we can speak from our own experience. As a maintainer of Cilium, probably the biggest eBPF program that currently exists, we invested a lot into a troubleshooting and debugging layer. And it's fantastic because we were able to leverage the tracing layer of eBPF. So one of the prime use cases of eBPF is tracing. And when you do tracing, you hook into user space applications or into kernel functions, and then you emit some event. For example, I have observed something, or you want to emit a string or something, and then show that in user space. And for this, the so-called perf ring buffer exists. It's a ring buffer that allows an eBPF program to send events to user space in a very efficient manner, and for user space to retrieve those events and, for example, print them. It's an arbitrary generic ring buffer. It could be messages. It could be really anything. We are specifically using that to basically bake in debugging. So it means that in the code, we can basically print debug messages anywhere we want them, and then on the fly actually enable this. This is very interesting because of the nature of eBPF. It's possible to atomically replace programs. We can, even in a production environment, actually enable data path troubleshooting messages. And very similar to how a kernel developer would do debugging with print K statements, we can do that, but actually without recompiling the kernel or without restarting it. So that allowed us to do a lot of fantastic troubleshooting when needed. Because if you run in the kernel, you can't simply attach a debugger. It is possible, but it's not as easy as it is for a user space application.
Well, yeah, because you're trying to hook into the underlying operating system, and now when you hook a debugger to things, it messes everything up and gets all weird.
Yeah, and in a lot of cases, you can't even just sleep and break, right? If you are processing a network packet, you can't just, okay, let's wait. That option does not exist. You would break your kernel. Or if you're doing a system call, in a system call, you could actually sleep, right? That's actually feasible. the application doing the system call would then sleep and stall, and it would look like it deadlocked or something. But that would actually be okay. But for a lot of the other eBPF program usages, it's not possible to even just break and stop as a typical debugger would do.
Okay, and you were kind of mentioning, this debug layer and being able to atomically replace programs. How are you actually doing that atomic replacement in eBPF?
Yeah, so the really fantastic property of eBPF is that the program and its state is separate. So if you look at a typical application, when you load the program, and if you want to replace the program of your user space process, you have to restart the entire program, the process. And you will also lose all of its memory. You will lose the stack. You will lose like everything. Like you will start from scratch. With BPF, this is different because you will also lose the stack, right? Because the stack only exists for one invocation of the program. But between invocations of the program, you can replace the program atomically while the map state prevails, which means you can, for example, collect statistics or maintain a connection tracking table in BPF or have firewall rules in the map and then replace the program with the BPF system call atomically while the state still persists, which means you can apply hot fixes, you can upgrade your programs without actually disrupting anything that's going on.
So almost if you had, let's say, a debug switch in your control plane, you could say, flip this into debug mode. It'll swap out and load the debug version of your BPF code. And because your map is pinned, as we discussed earlier, that doesn't get thrown away because that's the responsibility of the program to clean up. Instead, now you have this debugging version. But how does that work with that ring buffer that you were discussing earlier? Does that get cleared or is that new for each instance of a program, or does that actually persist?
That persists as well. A ring buffer is just another BPF map as well. So that ring buffer is always there as well.
So essentially, because that's still there, again, as you kind of said, you're not losing anything by swapping it out to the debug version. Now, the buffer might just fill up a little more because you have more debug messages coming out.
Yeah, and even because it's a ring buffer, even if the BPF program is very quick and may process, let's say, only a couple of thousand packets per second, it may still emit hundreds of thousands of debug messages. The user space program doesn't have to be quick enough to read everything in real time. It can buffer everything in a ring buffer and then at a later stage read it, because the user space program may not be scheduled on the CPU at the same time as the BPF program is running. So this allows for a kind of a single switch that kind of, I need debugging now, maybe for the next 10 packets, and then disable it again, because all I need is a couple of traces to figure out what's going on in my program. You can even do things like, only because you can atomically replace the program, if you know the failure scenario, you can only enable the debugging if a packet is arriving matching that specific failure scenario. This is how we have, for example, tracked down box around IPv6 extension headers. We would have logic in there that would only emit the traces if packets with IPv6 extension headers would be received, and so on. It's actually been fantastic, at least from a perspective of a Linux kernel developer, where that's kind of our standard, right? Like from a perspective of let's say a Java application developer, it's still very difficult to debug an eBPF program. But compared to kernel development, it's actually very handy.
Yeah, when you're used to having that user space, APM, application performance monitor, reading everything in your code, and you just go to a web interface and see runtimes for each function. It's a lot easier than trying to write a program to handle some ring buffers and maps and all that kind of stuff. So I kind of want to change directions a little bit here and start talking about some of the use cases that we have with eBPF. I mean, we've discussed a bunch of them so far, anything from, XDP being used in the NICs and even projects like Cilium and some of the use cases you guys fulfill. But I do want to talk, as we've moved into a more containerized world, how do you get eBPF to understand that concept of a container?
That's interesting, because the Linux kernel, and this may be a surprise, the Linux kernel does not actually know what a container is. The Linux kernel understands C groups, namespaces, process boundaries, process forking, and so on, but it doesn't actually understand container. Container uses all of what I just mentioned to create like container isolation, or the concept of a container. So you cannot go on and say, kernel, give me give me the memory usage of container with container ID X. The kernel does not know what container ID X is. You would need to translate container ID X into the actual C group ID and then ask the kernel, okay, this container is using this C group for memory consumption or for memory isolation. Show me the configuration or show me the usage and so on. And this is where eBPF comes in and can make the kernel indirectly aware of concepts like Kubernetes, container, microservices, and so on, by allowing it to, for example, do packet filtering or system call filtering with the awareness of container ID, or containers or pods and so on, by encoding that as part of eBPF programs. That's making it so powerful. The reason why that's even needed in the first place is because typically the time between writing a kernel feature and by the time it gets available is multiple years. Like it's often 5+ years. Like somebody writes a kernel feature, and then by the time that kernel release gets into the hand of users, it's just so long that it's very rare that the kernel is actually up to date in terms of use cases. The kernel that you run right now, it's probably not been written with your current use cases in mind. And eBPF programs, you can obviously load any program that you want, which means you can bridge that gap. This is what's making it so powerful.
Yeah, so it's giving you that flexibility that you don't actually get with kernel development because of the fact that kernel development is delayed. It takes forever to get a patch in. And then even once you have that in, now it has to be rolled out to all the distributions. And not everybody's running the latest version of the kernel in their distribution and, every other what if scenario. But just kind of circling back, so you mentioned the concept of namespaces, C groups, all that kind of stuff. And as you kind of mentioned, probably most software engineers aren't going to know what that is. They might understand the concept of a container, but they might not know how that works at the lower kernel level. Can you kind of dive into that a little bit and explain it?
Sure. So I think containers are two aspects. Like one is the container image, which I will not cover, kind of the packaging, shipping the entire dependencies and so on. That's one aspect. And then the other aspect is the deployment form, like how it actually runs on the system. And the migration or the movement away from virtual machines as the deployment or kind of the isolation form to a container, in which case the kernel becomes responsible to negotiate the resources between containers, because obviously we're running multiple containers on a single system, which means somebody needs to be aware and in charge of, for example, making sure that one container cannot use all of the memory of the entire system or all of the CPU on the system, or who ensures that the networking of one container or like one application running in a container cannot just access the other application in another container on the same system, because from a networking perspective, that would obviously be possible if you don't do the isolation. For this purpose, the concept of namespaces has been created, actually much longer than containers exist as a concept. It's been many years. And then later on, the concept of C groups have been introduced as well. And it's all about making the Linux kernel multi-tenant, so multiple applications, multiple tenants can operate a single system without necessarily trusting each other. And by providing isolation on all levels, CPU, memory, networking, storage, file system, mounts, users, and so on.
Yeah, and this is where that benefit of the kernel almost being that choke point helps, because now it can filter syscalls that are accessing these items based on those C groups. And that's where, you can start leveraging eBPF to hook into that. But to kind of dive into some examples here. So how would you roll out eBPF in something like a microservice environment, for things like observability, networking, security? I know that's a lot of what Cilium is actually capable of doing.
Yes, so Cilium is a networking and security layer specifically for Kubernetes Cloud Native. And for networking, we can use the specific example of Kubernetes, which I guess is the most dominant container platform right now. You typically come as a so-called CNI plugin, like container networking interface. At that point, you are the component that is responsible for allowing containers to communicate with each other, like container to container, and also how to communicate to the outside world and how to allow the outside world to talk to containers. And in that sense, the CNI plugin actually has a lot of freedom on how to do this specifically. Most CNI plugins will use so-called virtual Ethernet pairs to create a virtual Ethernet cable, basically, between the network namespace of the container and what's called the host namespace. So like there's always like namespaces and C groups are always like come in the form of a tree. So you have like an init or a host namespace or a C group, and then you can go down into multiple levels. So you need to bridge the container namespace with the actual host, and then also bridge that out to the outside world. This is what the CNI does, and that gives the opportunity to attach an eBPF program to that virtual Ethernet cable, so it sees and controls all of the network packets that come in and out of a container. And for the case of system calls, you would typically attach the eBPF program to the C group. So all of the system calls being done in the concept of that C group, which then is equivalent to all of the system calls being done in that container, would go through that eBPF program as well. So you're using the kernel level constructs which are used to build containers as a way to integrate into containers.
Okay, and that's almost something like where Falco would almost hook into that system. That's using that eBPF and filtering based on those C groups and then looking at the specific syscalls coming from those specific containers.
Exactly, yes.
Yeah, and back on episode 341, I know we discussed a little bit about container networking, and on 290, we discussed some stuff around Docker and security and some of this lower level stuff and how this isolation works. But just to kind of dive into some specific examples here, with observability, we've kind of mentioned tracing. Would I hook my eBPF program into some type of overall like distributed tracing framework, or is it really just like pod specific for Kubernetes, for example?
Both, actually. So in the case of Cilium, we offer kind of all the way from low-level network flow logs, what you would expect from a typical network layer, all the way into higher-level tracing languages such as open tracing information that you would typically only expect from the application levels, like understanding of HTTP calls, Kafka topics, gRPC calls, and so on, DNS information, like high level, like clearly beyond what you would typically get from a network observability platform. But also we can do both, and that's a really powerful aspect of eBPF, because we can combine what we see on the network level from a packet perspective, but that we can also hook into, for example, the socket layer and understand the data that an application sends or receives, or even instrument Envoy, which is the layer 4 proxy that Cilium uses for some of the HTTP parsing, and get information from there as well. That's the true power of it, because eBPF can be used to glue everything together and then combine all of that information to provide a very meaningful visibility layer that goes well beyond what what typically existed so far.
Yeah, so you're almost getting that full stack monitoring capability from an observability perspective. So this would almost replace, or at least supplement, something like putting like an APM library into my specific code, or having all of my engineers implement OpenTrace. This is almost that I can get this same level of observability without having to make every engineer rewrite every piece of code.
Yeah, absolutely. And the really powerful part here is that this will work even for applications that you don't want to change anymore, right? In a lot of scenarios, you may not even have access to the source code. So the option, it's not the decision whether you want to change or don't want to change your application. You just don't. For some applications, you can't. You're running a proprietary piece of code, and you still want to instrument it, or you want to understand what type of HTTP calls are going on, what is the latency, how long does it take for a REST API to respond, and maybe you don't have access to the source because maybe you cannot add instrumentation code. And this is where eBPF comes in. And you can do this at multiple levels. You can combine the visibility you have at the network layer and then also instrument with eBPF, for example, the HTTP layer of the application, such as the HTTP Go library. And, for example, add trace points to figure out how long does it take to decode and parse an HTTP header, how long did it take for the application to respond, and so on, and combine all of that so you can answer questions. Is the application slow? Is the network slow? Is it TCP? Is it like overall CPU on the system? You can correlate what you see in terms of latency with, for example, TCP retransmission, so you understand whether maybe it's a lossy network. And this is the really interesting part. You can combine all of this, which gives you a very compelling visibility layer and like a true answer, which was just not available for eBPF. Not because the information did not exist, but simply it was spread across multiple systems typically.
Yeah, so how does this compare to something like an Istio service mesh?
That's an interesting question. We get that a lot, and there's a lot of overlap in kind of the values we provide. Like Service Mesh, Cilium, the ask or the promise is to provide visibility into applications, network service calls, and so on in a transparent manner. The implementation is very different. Like Service Mesh or Istio typically uses what's called sidecar proxies to inject proxies into the application pods and to extract visibility from there. The outcome is similar. That you get a transparent, you get a piece of code that sits in there transparently and can observe and control. Like in the Service Mesh Istio case, it's the sidecar. For Cilium, it's the eBPF program. The big difference is that there's obviously like a latency and an overall performance overhead between sidecar and eBPF, and we could talk a long time about that. But I think the even more fundamental difference is that Service Mesh typically relies on, for a lot of the functionality to kind of have end-to-end visibility, you need to have the sidecar proxies on both sides. For example, mutual TLS will not work if you don't have sidecars on both sides. With a lot of what Cilium is doing, because it's integrating on the kernel level, it does not require to have this. It does not require to manage both sides. You can easily do, for example, HTTP latency tracing while only running on one side of the connection. So only, for example, the client is somewhere else and you're not controlling the client. You can still measure HTTP latencies, for example. But overall, I think you can get the same or very similar information from both systems.
Yeah, and we've discussed, I think, back in episode 361, more on the Istio service mesh specifically. But as you kind of mentioned, it's all dependent on the proxy and the sidecar being able to work on both ends of the connection. And you get some of those benefits like, mutual TLS and some of those other security benefits. But as you mentioned, if you don't control the client, you're missing half the connection. So there's not really as much value there. And you're also adding like a latency overhead for all of these connection calls. Whereas with eBPF, I mean, as you mentioned earlier, it's near execution time.
Exactly. And I think the other thing to mention here is that the sidecar will only see like layer 4 and up, right? Like you don't have any visibility what's going on in the kernel. So you cannot correlate this information with, for example, network visibility or network layer information or TCP retransmissions and so on. You cannot answer the question whether it's network or application. All you see is kind of sidecar and up. There's also just a complexity overhead. I think the real benefit from like the eBPF model is that from a user perspective, nothing changes, right? Like the kernel is, to most people, it's basically already this huge big black box, and you're adding programs into the kernel, and it will do or kind of extract visibilities. You're not changing anything from how it looks to the end user. Whereas in the service mesh model, you're definitely changing in way. I mean, the sidecar is visible to application developers. It's running as part of the Kubernetes pod, which is typically owned by the application team. So it's definitely visible to some extent. And you're changing how the network flows are happening. And so it's definitely a more involved architectural change. And that's I don't want to bash service mesh too much. I think a lot of what service mesh is bringing is actually absolutely fantastic. I'm not 100% in agreement with the current sidecar implementation model. I think what we will see longer term is that the control plane and the user interfaces of service mesh will continue to exist. And I think we'll see more and more of the sidecar or more and more of the service mesh data plane to be implemented by something like Cilium or eBPF, where you still get the same high-level benefits, but you will have a more efficient data plane implementation.
Yeah, so you'll essentially start to see, as I kind of mentioned, like with the mutual TLS, like that might still exist within that service mesh layer. Some of the, pod authentication might still live within that control plane service mesh. But when we start talking about like lower level observability and application tracing and network tracing, that's going to start to maybe migrate into the closer to the kernel world where, you're preserving kind of the black box layer between, the kernel and user space.
Mm-hmm. Absolutely. I think there's even a more fundamental difference here, which is, or like another very fundamental interesting point, which is Cilium can, for example, do what's called policy-driven TLS termination. So you can terminate the TLS connection on behalf of the application. You can also do this with service mesh. There's a difference here, though, that if you do this as part of a sidecar, you are within the bounds of the pod, within the bounds of what's owned by the application. So if that application gets compromised in some way, whatever the sidecar is doing is also gets compromised. In the case of Cilium and with eBPF, we can do this outside of the pod. So it's outside of the control of the application, which is really interesting if you are running untrusted workloads. So if you cannot fully trust the workloads that you're running in your clusters, but you still need, for example, TLS termination, or you want token injection and want to force certain services to use certificates or keys in order to access an external service. With eBPF, we can do this outside of the pod, which means you can run fully untrusted workloads and don't have to expose any secrets or certificates to them.
Okay, so when you get the proprietary black box from your vendor, you can still, inject some of the security that you want in there.
Exactly. Yeah, that's a common use case.
So I just want to wrap up the show now and start closing this out. So what are some resources you would direct people to if they want to learn more about eBPF, they want to learn more about XDP, writing this code, something like Cilium and where that fits in?
Yeah, so I think the best starting point is a website called eBPF.io. It's a community-owned website that we have launched a couple of months ago. It will give you an overview of eBPF, basically everything we covered today, and also list all of the projects that exist in the eBPF ecosystem. So if you're interested in tracing, what are the projects that exist around tracing? If you want system call security, what projects exist? If you need container networking, what are the projects that exist, and so on. We also have a eBPF Slack community, ebpf.io/Slack. That link is also on eBPF.io. Hundreds of eBPF developers or other people learning about or with an intent to learn about eBPF in our Slack community, helping each other out. And then we have also covered Cilium. So you can find more information about Cilium on cilium.io. A source of great talks is the eBPF Summit, which we hosted a couple of weeks back. Dozens of really amazing talks about open source projects in eBPF in the eBPF space. You can also find that on eBPF.io. That's definitely, there's I think great intro level talks to low level eBPF verifier internals, like really anything that your heart could ever wish for in the eBPF space.
Yeah, I was watching some of those summit talks. There's actually a really good keynote from the recent one on just some basics of writing a basic eBPF program. And that might be good for our listeners if they want to start getting exposed to what the code actually looks like. So what other stuff are you working on now? Any additional research in the area?
There's so much going on in eBPF right now that I think it would be unfair to mention just a couple. I think in general, we're seeing the space is literally exploding right now. We're seeing huge investments into Linux security modules, which is the overall runtime security layer that the kernel provides. Google is heavily investing in that. I think that's super interesting. We're seeing eBPF obviously in the overall security space, in the visibility space, in the networking space. We're seeing more and more tracing tools come up. There was, I think, Pixie Labs just launched a couple of weeks back as well with really interesting topics. There's just a lot going on right now. It's really hard to even keep track of what's going on. I think the promise is huge, and a lot of people are just starting to realize the full potential of it. And we'll see a ton of stuff getting created by eBPF. But again, I think it won't be that a lot of people will natively use eBPF. Like eBPF has been designed for kernel developers, and it will remain like that. But a lot of the higher level projects that are written on top of it will be very, very interesting to a lot of people.
Yes, it'll be like most things in open source. I'm going to start taking someone's already implemented project and then tweaking it as I need to for my environment. All right. Well, Thomas, thank you for coming on the show and discussing BPF and XDP and how we can leverage them for observability, networking, and security. I will definitely put links to those sites that you mentioned and some of the resources I used for research on this topic.
Awesome. This was great. Thanks a lot for having me, Justin.
This is Justin Beyer for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.